Hey everybody, thanks for coming to this talk. We have a really exciting topic about LLM training and the data and I/O layer. It's called Supercharging LLM Training with Mosaic StreamingDataset and also Lance. My name is Changshe. I'm the CEO and co-founder of LanceDB.
And hi, I'm Karan Jariwala, and I'm an engineering manager at Databricks Mosaic AI.
So real quick, I've been creating data tools for data science and machine learning for about 2 decades. I was one of the original co-authors of the Pandas library, and I've spent a bunch of time in big data and recommender systems land. And I started this new company called LanceDB about 2 years ago. We're the database for multi-modal AI. And these days I spent about equal time tweeting and coding. So you can go on Ship Talkers and look at your own ratio.
Hi, I'm a co-creator of Mosaic ML streaming dataset. And then before joining Mosaic, I was working at Amazon, and I was one of the founding engineers for the AWS Distributed Data Parallel Library, and I worked a lot on the model performance as well as the model explainability techniques.
Cool. So how many of you guys have not used DuckDB before, or have you not? Do you not know what DuckDB is? Okay. So DuckDB is a very popular in-process SQL engine, and the company to commercialize DuckDB is called MotherDuck, and Jordan's one of the co-founders, and he published a fairly popular blog post called "Big Data is Dead," and essentially his position is that even though companies store tons and tons of data in BigQuery, the working set of a particular query typically is fairly small enough for something like DuckDB to run. Now, our argument is actually it's not. AI, and especially multimodal AI, really changes the picture. So if you think about tabular data, where big data may be dead, maybe not, tabular data is about 150 bytes, 145 bytes per row. If you look at embeddings, right, they're about 4 kilobytes each. That's what, 25x. Images are even bigger, and videos, and 50 megabytes is actually a pretty small video. So that's about 350,000 times bigger than the average tabular data row. So not only is big data back, it's also way bigger. And moreover, data, because of generative AI, data isn't just being manually collected by explicit user action. It's actually being generated at thousands of tokens per second. So the two combined really pushes scale of your data through the roof. Training data for AI also increases a lot. So how many of you were at the keynote where Fei-Fei Li was talking about the evolution of the training data, right, and the ImageNet challenges and things like that? So if you look through that history, right, the earliest data sets were like CFAR10, CFAR100, which was around like 160 megabytes or so. ImageNet was around 150 gigabytes, right? The typical LLM is trained on about 1 to 10 terabytes of data for, text. Image and video models are something like on the order of like petabytes, I think. And so as we advance in our capabilities for AI, it also means our training data becomes several orders of magnitude larger for every sort of step that we take. And this presents a bunch of different challenges. And the first, we'll talk about the challenges on the training side.
So what are different challenges that you see in the data preparation? So the few are like, first of all, distributed training. So you want to make sure that your data, you get distributed across a number of nodes, number of GPUs, and number of CPU workers. That's the one thing that you have come up with the logic. Otherwise, there'll be like a repeated data across the nodes. Another challenge is using the cloud storage. I mean, in today's nodes, we don't have that much of a storage space as part of the ephemeral storage. we only have a limited storage, and our data set is in like terabytes and petabytes of data. So the solution here is to use some sort of a cloud storage that we can efficiently download our data from and directly into a GPU nodes inside an ephemeral storage. Third challenge is convergence. This, I think, one of the maybe the biggest concern is how better your shuffling your data is. If you haven't shuffled your data well, then you'll see a lot of the loss spikes, convergence issues, and everything. So you want to make sure that your data shuffles really well. And the fourth thing is elastic resumption, which is if you have ever trained a large model training, you always find either there is a hardware failure or a software failure during the training, and you need some sort of a resumption logic to make sure that you resume from those trainings. So you'll do the checkpointing, and then you resume from the data loader state. So if you don't have that, then you'll waste a lot of time downloading the same data again, and you'll basically spin up the data loader to try to come to a stage which the model has not seen before. So as you can see, there is one note here where it says it took like 50 minutes to resume a training from checkpointing, and then 30 minutes itself just took fast forwarding the data loader. Now, what are some common issues? So when you do a model training, you often find sometimes that the GPUs are underutilized. And when you see that, one of the areas of concern is your data loader bottlenecked or not? Or is your data loader processing time is more than your model forward, backward, and optimize the step time? Another one is the high egress fees. So if you don't really pay attention to how you distribute your data across nodes and GPUs, you end up downloading tons of duplicated data across all the nodes, and that will incur like 5x or 10x of your egress cost. And the third thing is like duplication of samples. You really want to make sure that each GPU takes the unique number of samples or batches for the model training and not take a duplicated samples. If it takes, then it basically won't generalize the learning, but it tries to memorize the learnings. So these were like some of the issues and concerns on the large-scale distributed training. So that's why we built the streaming dataset library from ground up to address all of these issues. So right now, as of today, our streaming dataset library powers all of our Mosaic AI model training. That includes pre-training, fine-tuning, and others. And that also includes like a classical deep learning, whether it's regression or classification model or recommendation model, or take any LLMs or stable diffusion models. And we basically build it for a large-scale distributed training. And the streaming dataset is pretty much works seamlessly with all of our like Gen AI stack. So the Composer is our distributed training library. LLM Foundry is open source library specifically for training, fine-tuning, and evaluation of the LLM models. And the diffusion is the same for the image-based stable diffusion models. Now, what is streaming dataset? Streaming dataset is basically a drop-in replacement for a PyTorch iterable dataset. So we basically inherit the iterable dataset and we build a bunch of functionality on top of it. So if you have in your code, if you have a class called iterable dataset, you can just replace that with the streaming dataset and it should just work. So here is like a small, cool video. I can explain like what's going on here. So for any model training, like if you plan to use a streaming dataset, there are two-step process. First step is to take your data and convert that into an MDS format. So the MDS is a Mosaic data shard format, which is a binary file format, which we created for insanely like fast random access. And to get the data really fast. And it's basically a binary file format. So one sample consists of sort of a dictionary with a key value pair, and a key, you can call it as like a column name, and the value is actual data. And that data can be text, that data can be a JSON, that data can be an image, video, or any of those data. So you take your raw data set, convert that into an MDS format, let's say upload it to one of the cloud providers, and then the step 2 is to provide that part, and it will stream directly from the cloud provider into a GPU cluster. So as you can see up there, there are like different color boxes. So each color box acts as a shard file, and the shard file is a file which contains one or more samples. So the streaming dataset will calculate what shard will go to which GPU. So the GPU will prioritize the downloading of a sample which needed for the first batch so that you can start the training instantaneously. And as the first batch gets loaded, on the background, it keeps on downloading the shard file and keeps on loading the batches so that whenever the model requires a new batch, it's up and ready for the model to take on. So you won't see any data loader bottleneck here. So that's a very higher level overview of how a streaming dataset works. So what are some of the key features and benefit of a streaming dataset? So I would divide this into 3 different pillars. So the first one is the correctness. So what does it mean by deterministic sample ordering? So when you train a model, you want to make sure that your sample ordering across a global batch is deterministic, which means that let's say if you're training a model and you see some sort of failure, you have to resume that either on the same number of nodes or on the lesser number of nodes. If you don't have a deterministic sample ordering, you'll see a bunch like a spike loss, and that occurs because the sample order changed, and now you're seeing a repeated samples again. So a deterministic sample ordering is critically important for a large-scale model training. Disjoint sample automatically loaded across a logical machine means you want to separate out the shard file in such a way that all the GPUs will load the samples independently and does not have any dependence on each other for data loading. And the third thing we have is the shuffling. What we have seen during our experiment as well, the global shuffling plays a really important role for a model convergence. So let's say if you have a million row sample, you want to make sure that you do a global shuffling. Also, we do a first global shuffling as well as a second level of local shuffling to ensure that a model learns the behavior rather than it tries to memorize the certain component. Second pillar is the efficiency. So we download this the shard file that we have asynchronously in the background so that it does so for training to start. It does not require to have the whole data resized into your nodes or a GPU cluster. As soon as the first batch is ready to load, it will start the training. And the background, we keep on downloading the shard files. Streaming dataset also has a best-in-class compression algorithm. Why we need compression algorithm? The reason being is if your dataset is huge, you can use a compression algorithm to compress your data so that that incurs a less egress cost when downloading the data from cloud. Third thing, I spoke about, the streaming dataset has an MDS as one of the data format that we build for higher throughput and for the randomly fast access sample time. And the fourth one is fast resumption. So what does that mean, fast resumption? So you don't want to download the old data set which the model has already seen. So during the checkpointing, we save a model state, or we also save the data loader state information. So when you resume the training, it downloads the data loader state information and tries to calculate what are the number of samples that the model has already seen, because we support a deterministic sample ordering. And it's just basically skip all of those before sample. So the resumption happened here in just a few seconds rather than in minutes. So that's the benefit of using a streaming data set. And the third pillar we have is data security. So no data is like resides or stored permanently in our cluster. It stores an ephemeral storage. So if the training dies, data get lost. If you resume it, it will download again on the fly. Yeah. And I'll go to a few of the slides highlighting the same key points and benefits. So here, why the high throughput matters. As you can see, the diagram or the chart on the left, it shows there are like up and downs going on. So one of the behavior here is the data loader is actually a bottleneck where data loading process is slow as compared to a model forward pass and backward pass. So the model actually, the whole training actually stops for a few milli or microsecond or for a second, and there you see a drop in throughput. But the streaming data set, you don't see that because we do a lot of asynchronous download and we do a lot of like short download. And then we also support dataset mixing. You can mix multiple dataset on the fly, and then you can also control whether you want to upsample or downsample those datasets. This is a diagram of elastic determinism. As you can see, the first diagram, you just basically see the same loss curve, that patterns. So it shows the model has been trained on 1, 8, 16, all the way to 64 GPUs. The reason why you see this is because of the global number of samples that are same in a batch, in a global batch, I mean. And then the second diagram is where you see the loss does not follow is because of the variation in the number of samples. And the last thing is the mid-epoch resumption. As you can see, you can actually stop the training. So we demonstrated this using the cloud providers. So we started on Oracle as a cloud storage. We stopped the training. We resume on AWS. We stop the training, and then we resume on Google Cloud. You see the same loss curve that follows it. Okay, then what are some of the challenges on the streaming data set that are we are facing? So two main challenges are, one is the dataset filtration. So the MDS is not really great as scanning the samples and filter out those samples. So which is like one of the challenges that we face. And the second thing is dataset joins. What happens if you want to mix a certain dataset? Let's say if you want to mix and create one unified, doing some sort of SQL query or all of those things. Those are right now not being supported in streaming dataset as of yet. And that leads to next one, which Cheng will gonna say about how Lance will solve some of this issue, or maybe all of these issues. Yeah.
Thank you. Yeah, so we've heard about streaming dataset, how it presents this high-level dataset API that's great for all the problems you encounter at scale in training. Now, with AI data, with scale, and also especially with multimodal data, it presents a lot of new challenges at a lower level for the storage layer. And when you filter, you need to do things like a fast scan. You need to scan through a lot of the data to pick out the rows that you want. And then to access those rows, you need to have random access. And when you shuffle the data, you also need random access. And then if you're training on multimodal data, you need to be able to manage large binary like images and videos effectively. And so no existing data format is good at all three of them. And so this is what I'm calling the new CAP theorem for AI data. And that's why we created Lance format, is to try to solve all three of those problems all at once. So the problem with having a system, data formats that are not good for all the workloads that you do is you end up in a state where the data stack for AI teams ends up being a bit of a Rube Goldberg with many single task systems. You may have Parquet in your data lake, then you have to offload some of that data into a vector database for search, and then you're loading some of that data into your training data infrastructure, and then for evaluation and for data curation, you have single task systems with data formats that's good just for that task. And so one, the problem is it's very expensive to maintain multiple copies of the data and to maintain multiple systems. Number two, it's way too complicated. So for a given AI engineer that has to go through that whole workflow, they have to know like 5 different systems and 3 different languages, and of course, lots of YAML. And it means your highest paid employees are busy doing sort of menial data tasks rather than focusing on what's really important. So if we don't fix this problem, I think this vision of a vector data lake is just a pipe dream, because they're just silos of data that's moved everywhere, and that you have to spend a lot of time wrangling them and keeping them synced up and together. So one specific example of this new cap theorem is a training run, right? So you heard from Karan, right? A typical training run, the workload will have, simplified workload is you filter it, right? Then you shuffle the data, and then you distribute that data, right? So filtering, right, is fast scans, shuffling is random access, distribution is maintaining the large blobs. So all three needs are in one workload. Now, what if we can't have it all? And of course, hopefully the answer is Lance. We call Lance a modern columnar format for AI. And so number one, it is a file format like Parquet. So it provides fast lookups, often at around 1,000 times faster than Parquet. It minimizes I/O for when you're loading large amounts of data. And we've actually, compared to Parquet, we've actually gotten rid of row groups, and you can store blobs inline for multi-modal data. Because with multi-modal data, if you have row groups, you can either tune it for your scalar, small data, metadata, or you can tune it for your large blob columns, but you can have both. So with row groups, you're sacrificing either random access performance or scan performance. Lance is also a table format. So there's a schema metadata and version metadata. So large operations to Lance is automatically versioned, and this gives you the ability to do time travel, which is great for reproducibility as you're training. So if you modify your data set or append to your data set and you find something went wrong in the next training run, it's very easy to roll back to a previously good state. And of course, it supports what we call zero copy schema evolution. So the speed of iteration and experimentation is very key in LLM training, right? So to be able to add features without having to copy of your data from object storage is really great for productivity, and it's also great for their infrastructure costs as well. And the third thing in Lance is indexing extensions. All right, so one is we have vector indices, IVF, PQ. We're adding more all the time. Scalar indices to make the filtering even faster for your metadata columns, and we're also adding full text columns as well. So the result of this is by using Lance format, you can go from this Rube Goldberg machine of single task systems to a simple single source of truth. So in one table, you can have metadata, you can have numeric and string and text data, you can have your large blobs like a video, and you can also have your embedding vectors. And you can run SQL workloads for the filtering, you can run PyTorch training by connecting it to a PyTorch dataset or data loader, and you can run a vector search and similarity search on top of that if you've generated a vector index. So it's a single source of truth for EDA training and feature engineering. So the largest data set we've seen in the wild for Lance is about 10 petabytes, supports billion scale vector search. I think the most vectors we've seen is around like 5 billion or so. And right now it's used by leading Gen AI companies, training models, from text, images, and also video. The most interesting thing about the indexing feature in Lance is that it makes every single Lance dataset also a vector database, so that instead of having to copy your data into a vector database, it's just a file, right? So it's portable indices that live with the data, just like with Delta Lake, you have portable metadata and schema evolution and manifests that live with the data. With Lance, you get that plus indices that live with the data. The vector indices in Lance are disk-based so that it can scale much faster, much bigger, without requiring a lot of memory, and without having to tie together the compute and the storage. So it allows us to scale much bigger at a much, much more cost-efficient way. The indexing also allows us to achieve much faster pushdowns. So instead of having to scan, even with stats-based pruning, you're still scanning through a lot of data, but with what we call scalar indices, essentially like B trees or bitmaps, you can achieve even faster random lookups and filtering. And of course, the indexing only makes sense when you support random access. So it's those benefits don't come up unless you're able to essentially satisfy that cap theorem for AI data. All right, cool. The Databricks Mosaic team and Lance are going to be working together in the future to integrate the two. So streaming dataset solves really hard problems with loading or training data, shuffling, resumes, and things like that. Lance solves hard storage performance problems for very large scale and also multimodal datasets. Streaming dataset can work with many data formats under the hood, of course. And so we're going to be putting the two together to deliver even better workflows for training on very, very large AI datasets. So if you sort of zoom out a little bit, what we're essentially trying to build together is we call it composable data systems for AI, so that Lance and streaming dataset can work together, but through essentially the Apache Arrow interface, it brings into the ecosystem all of your favorite data tools, from DuckDB, Polars and Daft, to PyTorch and Hugging Face for ML folks, to Ray and Spark and Trino for really large scale queries and data preparation workloads. Right. So thank you very much for coming to our talk. I think on the left you'll see a QR code for the Mosaic AI Slack community. And we'll be sharing, these slides will be available, so some of these links you can go to the presentations and the GitHub for Mosaic ML. And on the right is the QR code for the Lance CB Discord community. And we are just releasing the beta for Lance V2, so come and kick the tires and drop us a note on Discord or on GitHub. And I think we're both hiring, so.
Yeah.